back to our lectures on quantum field theory. This is chapter 6 and part 2 of the chapter. And by the way, please read Quantum Field Theory by Michio Kaku, Quantum Field Theory by Mandel and Shaw, and Relativistic Quantum Mechanics and Field Theory by F. Gross if you have the chance, along with this lecture. Having discussed the Dirac equation and its properties together with its Dirac matrices and as the traces of the Dirac matrices, we will now be proceeding to solutions of the Dirac equations. Dirac field equation. So here we introduce two new components of the Dirac field, and these components are the particle component and the antiparticle component, U which is for particle and V is for antiparticle. So this is your spinner, this is your U and your V, and these are your phi. By the way, please note that this is a vector, so you have spinners here, and normally or usually this wave function is normalized, so you have normalization coefficients multiplied to, like here for U and U, that would be 1 over square root of 2, 1 over square root of 2, as well as for V and V's, V1 and V2. So it will be very easy to find the solutions of the Dirac equation if the momentum space is considered, since the single spatial derivative will be converted into momentum and an algebraic relationship will be arrived at. So we will consider our Fourier expansion of the Dirac field, which is of this form. We will know later on the importance of this 2 pi to the fourth. But for now, you have Dirac field, which is your phi x, and it's actually just an integral of your field in terms of momentum. Of course, this is normal in the field, and the whole spectrum of momentum is considered here for k, and well, of course, this is integrated to the fourth power. Now, if we go back to our Dirac equation here, and if we use the Fourier expansion of the field, it will lead to this one. So you have the first term of the Dirac equation. So you just this is I gamma nu derivative nu of phi, and then you have generalized derivative, so when this is just a dummy, you can change mu into nu. So here, this is your field, and so you can put this inside. Your mu can be considered just a constant, and your generalized derivative commutes with your integral, so you can put them inside. And by the way, you only get the derivative of the exponential of I k mu x mu, because your psi is not a function of x mu. So you will finally have your I gamma mu, a derivative nu psi is equal to this one here. So that's the first term in the Dirac equation. The other term is this one. So m will just be a constant, so you can go in and out of integral at any time. So you can put m here, so this is your m psi. So if you subtract this from here, you will get the Dirac equation, and that is equal to 0. So you will have these terms. And so this is 0. This one here is 0. So the only way it can be 0 is when your integrand is 0. So therefore this must also be 0. So you now have gamma nu k nu psi k minus m psi k. Now this is in momentum space, equivalent of the Dirac equation. Look, you have momentum instead of the space. And of course, using the usual representation of momentum as a derivative in position space. Now we'll take a look at the individual terms of the equation, the new equation that we have, which is just of course the Dirac equation in momentum space. And recall that you have 4 gammas, but actually 5 gammas, but the gamma 5 is just a product of the other 4. So first we have this one, gamma 0 k0 psi. So you just have this, and of course your m psi for that would just be the same for all. Next is this one, and this one for the 3rd gamma, and for the 4th gamma this one. So if you put all of them together, that would just be this. These are just equivalent to 2 coupled equation if you do the operation of matrices. By the way, we can let this as k to simplify things. So for this to be true, the determinant of k must be equal to 0. So by the way, if you get the determinant of this would just be equal to this one. This is supposedly equal to 0, but the form is this one here. So let's calculate what this is. So if we do that, we can get the dot product of k sigma times k sigma, which is this one, k dot sigma I mean. So you have how many terms here? You have 9 terms, and of course each of these terms are containing products of k, 2k's and sigmas. So there are 3 terms which are products of the same k and the same sigma, but the rest are combinations of 1 2 2 3 and 3 1, which is actually just if you simplify them, you will have these ones, and these are just equal to Kronecker delta, which is just zero, of course, if you have different indices. So finally, what's left is your k square, k vector k, or momentum, that sigma square of that is just your momentum square. This is not the 4 momentum, that's just the 3 momentum. So therefore, this is now equal to, of course, 0, and this one is just the energy. So therefore, if you put that in the other side, like this one here, that is just the relationship, relativistic energy relationship. So working with units where h bar is equal to 1, your momentum is equal to p, and your k0, the fourth part of the the first part of the form momentum, would just be the energy. So if we write the energy in terms of the frequency, we have this one. Therefore, if we take the square root of this one, we will be able to get this. So the energy is clearly positive and negative. And so we're still having some energy that's below 0, which is, of course, in quantum mechanics not allowed. But we have to accept the fact that it's now interpreted as antiparticles having positive energy. Now, if we have omega k greater than 0, or energy greater than 0, the solution is a positive frequency solution. Otherwise, it has a negative energy frequency solution. So the positive energy solution is interpreted as corresponding to particles with positive energy, and the negative energy solutions correspond to antiparticles with positive energy. By the way, here is some notes on Dirac's prediction. I will just read them. Dirac predicted their existence of a notion of a sea of negative energies or energy states. However, his logic to predict the existence of antiparticle is wrong. There is no Dirac sea. It is recommended that more readings about this in most quantum field theory texts. So, having dealt with solutions of the Dirac equation, we'll now go to the free space solution. So this is the free space solution of the Dirac equation. Now we're discussing if a particle is observed in its rest frame, or simply say at rest, then it has no motion and no momentum. So this means that the spatial derivative in the Dirac equation can be discarded. And we will use this case to develop a free space solution for the particle at rest, and with that we'll do a Lorentz boost to find the solution for a particle with arbitrary momentum. In the case where the particle is at rest, so our Dirac equation will be reduced to this one. No more space, only gamma 0. No more gamma 1, 2, and 3. So taking our field to be this one, composed of particle and antiparticle. So now If we substitute that here, and by the way, u dot is partial differential of u with respect to time, and of course that would be similar for v. And so doing the same operation for m, and finally we will have this equation here. So we have two elementary differential equations, one dealing with particles and the other dealing with antiparticles. So so if you solve them, this will just have solutions of this form. If you would recall non-relativistic quantum mechanics, a free space solution has a time dependence of the form e to the negative iet. So if we make some comparison, and in this case for the rest energy, the u correspondence is this one here. This means that E is equal to m. Actually this is equal to mc squared, but for natural units you have c equals to 1, and for the antiparticles you have also this. Therefore u is a two-component spinner representing a particle, while v is a two-component spinner representing an antiparticle. These are two-component objects because this equation describes spin one-half particles. In quantum mechanics, you have for spin one-half particles, you have it represented by this one, which is just alpha and beta as the two components of the spinner. Alpha is the amplitude to find the particle spin up, and the other one, beta, is for finding the particle probability amplitude of finding the particle that is spin down. So as I've said earlier, in quantum field theory, it could be the upper one is a particle and the lower one could be antiparticle. By the way, they could be interchanged, but this is just the convention that we are using as of the moment. Particle and antiparticle. But in quantum mechanics, you have spin up and spin down, as it was the energy level to the number of particles in quantum field theory and quantum mechanics and quantum field theory respectively. Now consider a particle moving with arbitrary momentum p. This is for momentum, and use the scalar product here with the space x. So this is a free space solution, so there are going to be plane waves. So use the rest frame solution to guess at a solution for a particle with momentum p, and use this one here. So we will have for u and v, for particle we have this, and for antiparticle we have this. So if we use the Dirac equation again, you will be able to get this for particle and this one for antiparticle. And if you get the product of this, this will just be equal to that one here. And by the way, these mu are just dummy indices, so these both of these terms are just equal, so this is just equal to 0. And finally we have this one here. So this is an identity equal to 2g mu nu. So you can write this as mu multiplied to this one, you can have p mu. The 2 here will be cancelled by the normalization coefficient. So if you have a particle like u, for example, you will have 1 over square root of 2 for the upper part of u, and for the lower part you have also 1 over square root of 2. So you can cancel this 2, so that finally you'll be able to actually get this. This one is just the inner product of p mu, and so you will have this one. So the product is actually equal to 0, but then again it is expected because of the Dirac equation. So these are the solution for free space. I mean, for a moment, I mean, you have solutions for free space where your momentum is 0, and then you will have the solution for particle with momentum p, and antiparticle with momentum p. By the way, those are the initial states. I mean, those are the states where the particle is still at rest. So the initial states are given by ordinary spin up and spin down states, freely chosen or taken. For example, this one. Now we will go to boosts, rotations, and helicity. So Dirac matrices have been written down, and their defining anti-commutation relation is given by this. Sorry for that. Given by that. Now, how will we use them to generate boosts and rotations for spin 1/2 particles? For Lorentz algebra, it requires that the operators J, mu, nu must be determined so that they satisfy this. But this is a tensor defined by this one here. Let's see how are these tensors being used later on. So for a spin 1/2 particle, the generator of a Lorentz boost in the jth direction is given by this. And the generator for a rotation for a spin 1/2 particle, therefore, is this one. That is if you would use the definitions of the gamma earlier. Now we let sigma for that matrix, which is given by this one, in vector form. So that can be used to define the helicity operator, which is just how closely it is aligned with the particle with a spin of a particle to the direction of motion. I mean, helicity determines how closely aligned the spin of a particle is with its direction of motion. The direction of a particle's motion is given by its spatial momentum vector p. So the helicity operator can be written in terms of h, which is given by this expression here. Just the sigma, the vector sigma, capital sigma, dotted with the spatial momentum vector. That is the helicity operator, thus we are using h here. Now let's go to Vial Spinner. The chiral representation is useful in considering a special type of spinner known as the Vial Spinner. And by the way, you have the Dirac spinner also, which was discussed earlier. In the chiral representation, the Dirac matrices are represented by this. While for the Dirac representation, the Dirac matrices are written differently, but they remain traceless. So you can review that, and you can see that in the previous lectures, and maybe even at the start of this lecture. Also, in the chiral representation, you have this one, and so your p slash would be given by this. This is of course different from before, as p slash was written in this form in the Dirac representation. The components psi L and psi R will be the left-handed and right-handed spinners, and like Q and V, these two are two component spinners. The term chiral representation is used because these components are eigenstates of the Helicity operator. So this thing you have to remember. So when m is 0, the Dirac equation will be just this part, no second term, and in matrix form it is just this. So you will have these equations if you do the matrix operation, and of course this is just equal to p squared, and so the eigenvalue here is 0. So finally you will see that the energy is just the momentum. For the right-handed spinner, you will have the same, only that the energy is negative. I mean, not negative but positive. So if you have so anyway, this is your with negative momentum. So writing the Helicity operators as sigma dot p, the left and right-handed spinners can satisfy the eigenvalue equations, which are given by this and this one. By the way, the Vial spinners are also eigenstates of gamma 5. Now let's go to an example to illustrate more about the Vial spinner. So in this example, consider a massless Vial spinner and show that there are eigenstates of gamma 5 matrix given by this eigenvalue equation. So in the chiral representation we had this, and if we apply it to the Vial spinner, gamma 5 will just be this one and that one, and it will give you this, and your identity matrix applied to I will just give you the same spinner, and I minus gamma 5 psi will just be this. And so this will lead to this one, and of course if you do the calculation similarly for the right component of the Vial spinner or the right-handed particles, then you will be getting this expression. Now gamma 5, if you square it, it will just be the identity, and gamma 5 applied to the left-handed spinner or left-handed component of the spinner, you will have this one, and so you will have a negative Vial. This means that the eigenvalue of gamma 5 applied to the left-handed part of the spinner is you have an eigenvalue of -1, and for the right-handed you will have +1. So as a summary, the Dirac field equation was derived by Dirac in an attempt to get a relativistic equation with time and space on the same footing. while avoiding the negative probability densities associated with Klein-Gordon equation. The equation still has solutions with negative energy, which are a result of the fact that it describes antiparticles as well as antiparticles. So that's it for our second part of this chapter's discussion. So we will proceed with the next chapter, and I hope you've learned something in this particular lecture. See you in the next session, class.